For our next session, I invite Abhishek Chaudhary sir. Dr. Abhishek Chaudhary expertise leadership role in medical products and system innovation with focus on AI IoT from public health. He is a PhD holder in product design from Indian Institute of Sciences, IISc Bangalore. He pursued MSc Psychology, MBA Finance from Annamalai University and PG Diploma in Hospital Management in the year 2020. Sir has 20 plus years of product development experience and architected more than 15 projects including AI product design, electronics and firmware. He is a founder of Hindaway, a non-English programming system platform capable of robotic control design. He received a national IT award for the projects in 2005. He was the former founder and CEO for Indie Cybers, responsible for medical devices related to physiotherapy and rehabilitation. Sir was awarded IET Innovation from London, IEEE Indian Council Award in the year 2020. I now welcome Dr. Abhishek Chaudhary sir onto the dais for a session on HPC and LLMs.
All right, so since we are on record, thank you for such a nice introduction. I had a nice recollection, okay, that I did all of that, but just a clarification, never completed my PhD, dropped out 2 times, went to IISc a 3rd time, they did not allow a hat trick, so let's get on with the HPC for LLMs. Cheers, all right. So HPC in the context of large language models, what is HPC? We need to get into that. Now instead of saying HPC, if I said supercomputing, sounds wonderful. Wow, someone is talking about some big computer. The challenge with supercomputing as a term is, if I look back at something like when I published my first paper on the topic of AI 22 years back, a supercomputer was weaker, and that's why I'm carrying this around with me. It's a little odd. I'm not carrying any notes here. It's the same set of slides. The Cray, I think Cray 3 or 4 was there around that time, so would probably know that better. That had less computing capability in terms of all 3 elements, I'll come to that, than what our mobile phones have today. Give or take, there are elements that would have probably excelled in. So I tried to give a definition here. A little bit of help from ChatGPT was used, though I would recommend you not to try and use that for a last minute project submission as I faced. I was talking to it about a lot of topics and finally it failed. It has a context limit. I'll come to that and why do we need HPC, better HPC, that'll tell you about that. I'll read it out verbatim. What is it? It is about using advanced computers for enabling large language models. Large language models, the best introduction has been ChatGPT. Did ChatGPT or their organization, did they create large language models? They've done a lot of innovation, no doubt. They've done a lot of engineering, good work there. But it's not where it all started. There is a lot of history. If any of you go into a simple search on Google Scholar, you can find that. I'll not go deeper into that. But using supercomputing methods, I'll use the term HPC and supercomputing interchangeably. We are really talking about parallel computers. I have those slides, I'll get to those. Importance of HPC for accelerating training, inference, role of computational power in scaling LLMs. These topics sound big right now. What I'll do is over the next 30 minutes or so, I'll do a quick time check. It's around 3:20. So the next 10 minutes, let me delve a little deeper into HPC first. What is HPC? And then we'll talk about how do we use HPC for large language models. Theoretically, people would have us believe that a workstation with a GPU is good enough for training and inference. Why is it that we cannot implement and run something like GPT-4, at least not train it on our local systems? Even if you get a DGX-1, it is not sufficient. DGX-1, DGX-2, these are AI, custom-built AI supercomputers from NVIDIA. Let's look at this. Okay, by the way, I do have a nice video on supercomputing 101 on YouTube. You can share the presentation with the people later and they can get the link from here. I've taken some slides from here. So this is an overall picture and we are really looking at purely HPC first. And then we're going to look at what is LLM and how do we use LLM for HPC. Now, Essentially, when we look at supercomputing today, how it has become accessible, there was a time when supercomputing meant you go to big labs, you fill in requisition slips, and for me that used to be the Indian Institute of Science in Kolkata, and not being in one of the recognized government research labs meant, I'm talking in front of the masters here, so was leading one of the major organizations on that as a part of NIC and all, but it meant we fill out requisition slips and wait for the time to be allotted. There would be a lot of vetting. Those days are gone, more than 2 weeks back, 2 decades ago I'm talking about. Today we just log in, you have the interface, you go in there on the cloud, you have access to everything that you need. When I say everything, what is that everything? There are slides that will tell you about that. Now, that is why the word cloud appears here. Although, I will try and wear an engineer's hat here, because I will not delve into theory in the sense, it's not that I don't want to delve into that, but probably people in the academia are more familiar with the theory and the formulae and the methods that they go on. What I want to touch upon is really the field challenges that we face. How I like to describe myself, thank you for the nice introduction there, is I call myself like you have the people who tune automobiles, they do the tuning for that, apply a little grease here, apply a little, get their hands dirty. So we are like the tuning guys for supercomputers. We get our hands dirty here, hands dirty there. Just as an example, I'll tell you, while we stick on this, I'm assuming people here are familiar with infrastructure in general, otherwise I would have started from ABCs. Would you believe me that before we run a test run of any workload on a supercomputer, we actually warm up the system. We spend time to warm up the system to get it to a certain temperature so that the flow of electrons in the gates across the dies is at an optimal level. So even if the workload is not loading the system to that level, we actually do that. So this is the kind of the grease that we apply and get the numbers. What does it entail? Now behind the cloud, behind the APIs and interfaces, what do we have? Are we doing? Okay, I'm at good speed. So I'll move on to the next slide. This is what goes on. Scary, right? That's the way I wanted to go in. I mean, typically this is how we would define and declare what is your essentially the slide reads, I've reused the slides from my Supercomputer 101 course. So what this talks about is a typical data center deployment. Now when we talk about a data center, we don't use the word data center, it's too big, we say lab. So when I say we, as in the infrastructure industry, we don't use the term IT because IT typically is about the devices that people use, end user devices, we call ourselves the infrastructure. And this is a typical, I would say a deployment diagram, not something that a designer would deal with. This is something that a commissioning team would deal with. Not this part, this would be the block, where you have things as such, you have power, you have storage, you have switches, you have networking, but this is complex. This is not how we want to start. So we'll move on to the next slide and make it more complex. I'm sorry about that. The reason I'm doing this is, I want to give a breakdown from the bird's eye view level. This is the topmost bird's eye view level. What has happened? Essentially, the architecture diagram, etc. that we have has remained, and we have created what we call replica sites. The reason for this is, if you look at the title of this slide, disaster recovery and high availability. Why do we need this? Now I tried to set the expectation that I'll talk purely about the engineering aspects of this. Think of it today. ChatGPT is working, I'll make the slide a little easier. So we'll be talking about this. I don't want to leave those busy diagrams on. Think of it, something like ChatGPT, there are millions of users accessing it globally. We do that seamlessly. At the same time, we are giving it our prompts. It is processing it, giving us the results. How is it doing that for so many users? Okay, they are doing it, very good. What happens if there is a failure in a data center, in a specific lab where they are running it? How do they handle that? So these are very typical engineering issues that have to be handled. All right, you say, fine, millions of users, you make a million supercomputers. No, that's not practical. We have to look at the cost optimization, the compute cost optimization, price optimization, etc. that we talk about. Having said that, if we look back at this, what this essentially says is if this is your data center site and this goes down for any disaster, man-made, natural, what will happen is the entire workload will seamlessly deliver out of another one. That's called the disaster recovery scenario. The others, I'm touching upon these topics so that when we delve more into the LLM aspect, I don't have to go back to the supercomputing and the HPC aspects. The other is high availability. Now let's say when ChatGPT does do that at times, our servers are loaded and busy. If you have used it well enough, long enough, you will find those scenarios, and still kudos to those guys, to the team, OpenAI and the infrastructure team, how they've done it. Multiple users are logged in, and we're not talking about hundreds, we're not talking about thousands, we're talking about millions of users. How do you ensure that you have sufficient capability, sufficient provisioning, not over provisioned? Because if you're over provisioning, you are at the very least investing extra capex, capital investment, or you are spending more energy than you should be spending. So how do you do all of that? All of this comes into the picture. I don't want to go into deeper into this. I will be talking about implementing LLMs on HPC. I'm on the topic. But to have this perspective is very important, because when we are looking at it from, I told you about the Formula 1 pit, the person tuning the car. When you're in the garage and you're tuning the car, what is important is what is the price of my replacement part? What is the price of the grease I apply? How much time it will take? It has various terms like MTTR, MTBF, mean time to repair, mean time between failure, etc. All of those come in. Having said that, we are getting closer and closer. I will not go into the details of this, what these are. Essentially, what this means is they are the lower layers where you have the physical host, you have various firmware level innovations that we have to do. So, typically in our line of work, an operating system is referred to as an application. When we talk about threads, we are really talking about CPU threads. So at that level, there is a lot of work that has to be done at the firmware level, because what we do is we optimize. When I'm saying we, as in infrastructure people, we optimize by stealing time from the end user. When I say stealing time, your system management also has to happen within the context of the execution of the user's workload. So just to tell you that this gets deeper into this, and this can be a separate discussion. But for a beginning audience, what does it involve? All the layers we know from our computer architecture. We have the hardware, the operating system, kernel, system software, libraries on top of that. Somewhere in between, I should have probably put in the accelerator here. That's where your GPUs and all go in. Okay, that's what I kept for HPC. Now, this was like setting the groundwork, and I said 10 minutes. I think I've done within 10 minutes. Thank you. So we now know we have compute storage I/O. We have a lot of data center mumbo jumbo to be taken care of to ensure that millions of users are supported. The kind of timing requirement, service level, the user experience at the end of the day, that should be there, and various other factors which we call ilities, availability, reliability, uptime, etc. taken care of. Now, given this, essentially just about anything with a large user base has to be run on a supercomputer, quote unquote, HPC, parallel cluster, whatever fancy name you use for that, high performance computing basically. How do we use that for large language models? So sort of like 10 minutes of, none of them are working, or? Okay.
Enough time, you can take one.
Sure, sir. No, I was trying to take ChatGPT's help to organize all the thoughts, and what I did was I exceeded its context limit even in the GPT-4 version. So just like this link over here, which will take you, when you have this, to the YouTube video where I go deeper into supercomputer implementation and all. There is another thing that I did today, because a nice discussion had happened between me and ChatGPT. I really stopped. Okay, I'll take a little bit of a break to bring down the tempo a bit and also make it more friendly. I was just talking to ChatGPT, and I'm going to be using these terms like ChatGPT is an individual. Why do I say this? I've spent around 25 years, 26 now maybe, chasing what I prefer to call synthetic intelligence. There are various factors, and she mentioned a lot of things. I don't know if you mentioned I dropped out of medical school after a year and all. So just to make things light, I prefer to refer to it as a person. And I was talking to it about how we can actually make all of this technology accessible. And that has been the Hindavi project that she mentioned. Dr. Prabhu is aware of and has been mentoring us on some of them for a long time. How do we make it accessible? We'll cover that. See, at the end of the day, we are trying to ensure there is inclusivity, there is accessibility, and there is sustainability. So having said that, taking a little pause, let's get back into tech again. Infrastructure requirements for LLMs on HPC. Before that, let's just talk a little bit of a context. Training large language models on HPC. Now, for the want of a better diagram, and since I was carrying this, how many of you, can I have a show of hands? How many of you have actually tried out talking to ChatGPT? Have you spoken to ChatGPT? So, thank you. Others have not? Some of you there, yeah, good. You have not, you should do that. You have a smartphone, right? See, it will be something like this, and it works pretty good if my internet is fine. Hi, can you be my co-presenter for a session on explaining large language models? Let's see what it says. Okay, for the camera.
Absolutely, I'd love to help. What specific details or points do you want to cover about large language models in our presentation?
Okay, I'll talk to her later. So, where does it take us? Are we there already? The Turing test and God knows what. It's difficult to define. Honestly, very difficult to define, because essentially the Turing test, and some of you may have watched the movie Imitation Game. Earlier, we are at the ACM Hyderabad Deccan chapter sponsored event, and I remember my first 2 years of ACM membership, they sent me a nice mug, ceramic mug. I don't know if they send it these days. The first one had Charles Babbage. Any of you, Charles Babbage, guys, students here? What did he make? The diesel engine? No, the analytical engine, right? So, a mechanical implementation of the computer. Sorry, I was just kidding, don't get me wrong. The second year was Alan Turing. And why it is so important to talk about Alan's work, Turing's work, he sort of set the abstraction. Did he begin with that? There is a lot of academic discussion going on around that, and we are on the topic of this guy here, an AI, an LLM, whether it passes the Turing test, and how did it happen? They were the code breakers during World War II, I believe, and they worked on the Enigma, etc. It's there in the movie. Excuse me. What is not there is the work that he did. So after the war, he went to US. Which university was that? Princeton, I believe, sir. So he went there and he worked under Professor Church. Now, Professor Church had, before that, worked on Gödel's theorems. We are delving a little bit into automata theory and formal theoretical computer science, because that will help us with the next stages. Gödel said everything can be expressed as a number. I'm putting it in my words. What that means is, it is possible, I'm not talking about the incompleteness theorem that it cannot be proven, axioms cannot be proven within the system themselves, no. I'm talking about the method we call Gödelization. You take anything, you take two symbols, anything. Let's say this pointer here and the microphone. They can represent binary, actually they can represent, depending on states, they can go to a higher order encoding as well. That was Gödel's work, and he spoke about real rational numbers. Church extended that to just about any number system. The work that Turing did was essentially about, it wasn't, his entire work was not about computability. Computability, if you read his thesis, which is around 150 pages, a good read, there is just a chapter which talks about on general computability. He talks about reversible algebras. Okay, I don't want to lose the audience here. Theoretical computer science is always boring. What he did was he came up with the famous 7-tuple, which we call the Turing machine. Some of you who would remember from the computer science background, you'd remember your Turing machines. You have a tape, and on that you can read and write symbols, and by having specific operations, computing happens, like magic. It's not magic, it can be proven. Later on, during a discussion, during an interview with the BBC, he was asked, would these machines be able to show human level intelligence or intelligent behavior, however it was put. And what he said was that is where he came up with the imitation game. Academicians may argue whether that was the first instance or not, or whether he actually took an influence from someone else. What he said was, if you're at a party, you play a game where, depending on the question, you have the person behind a screen and you put that person certain questions and try and decide various demographies, whether it's a lady or a gentleman, how old he or she is. That was the idea. Later on, it was extended. If you put a system behind a screen, you talk to it, will you be able to tell whether it is a real human being or it is an artificial intelligence? That is the Turing test. We are already at a level where they can mimic things very well. So probably what we need is a super Turing test. We need a shifting definition where the bar keeps increasing. Having said that, we are talking about a system which satisfies the Turing test, in my opinion. We may argue, we may differ. It does a fairly good job, and I probably depend on it more than I depend on myself or some of my collaborators. So I think it's better than human in many aspects. It does not forget things. I had to look up the message, okay, I have to be there at 3:45. Trust me, with this guy on the phone, you'd not have to call me up multiple times. It would be here on time. Okay, so training large language models, back to the topic. Training large language models on HPC, what does it mean? You want to train this person, this kind of a model, you want to make your own AI. Around 5-6 years back, I used to run a session called AI in a day. So the amount of time I've done the talking by now, I would have expected all of you to have your laptops open and we'll be doing frameworks, data sets, models, and by the end of the day, you would have a chatbot that would do something fancy. Nowhere close to this. Will give you answers, dada, mama and all if you don't activate certain parameters. Best case, it will give you answers. We put in more layers. Bingo, one fine day in November 2022, one company comes out with a model and says, hey, it's available, accessible for public. Were we surprised in the corporate world? Yes, we were. Not because entirely of what they had done. As I've said, kudos to them for the kind of engineering they have done. Why we were surprised is, any guesses why we were surprised to see ChatGPT out there? One possibility, it came so soon. No, we've been dealing with similar things for a long time. I will not go into things which may not be public. We've been dealing with them for nearly close to a decade now. We were surprised, how on earth are they going to monetize this? Trust me, that's how business works. How on earth are they going to monetize, make it sustainable? Because why? I was talking about the data center technologies, the high performance computing. To train this kind of a 3 trillion parameter model, what you need is a mammoth. Now let me tell you what sort of a mammoth. In my last corporate role, I had the humble opportunity to architect the accelerator for what you today call the Watson hardware enablement layer. Went in to be the acceleration layer for Summit Sierra. Now let me tell you, what would my weekend system be like? I think it's a little bit of a quote-unquote advertisement for my previous employer, so I don't mind saying this here. It had 3 terabytes of memory. It had 294 cores. Now, we don't talk about CPUs anymore. A physical die has multiple cores. Those of you who are students here, if you're not familiar, get used to these terminology. It will show that, okay, you are interested in this and you're deeper into the domain. 294 cores, not 298, 294 specifically. That was a P9 version, Power 9 version. And it had 16 GPUs. of the V100, Victor 100, and it was not sufficient to load and run a ResNet 1 million. So over the weekends, what I would do is ensure when my colleagues are not using the systems, put 16 of them together. And yes, I could get something to work. ResNet is an image recognition model. Now, to give you an idea, when we put together a supercomputer of the size of Summit Sierra, each of these 3 terabyte modules with so many cores and all, systems not exactly like these but similar to these, were used, and around 9,000 of them were used. Anyone got a calculator? 294 into 9,000, 3 terabyte into 9,000. I don't know, you can give us the numbers later, but you get the idea. You get the idea. That's the kind of a mammoth we need to ensure that we are able to do this. Why? Optimizing training on HPC clusters or supercomputers. All right, a lot of things around the table, around the globe I've spoken about, not on the topic exactly. So let's get to that. This here is what you call the GPT architecture. Out of Wikipedia, thank you for the diagram. I did not have the time to take it off a research paper from OpenAI and then give the citations. Wikipedia is always easy. CC by essay, such and such URL, accessed on this date. Ideally, what I do is I go to Web Archive and save it over there. So those of you're familiar with Web Archive? You would be. Everyone just share it around because it's always helpful. They keep a history of what has been accessed. This here essentially is, we would have heard of transformers. Now, I'm trying to bring in 2-3 threads and I will be tying them as we move through this presentation in the next 30-40 minutes. I had to work on this. ChatGPT failed, I told you. And that's where I was left with a flat tire. Not literally, and that's why I was delayed, ma'am. Sorry. Okay. Now, this here, what you see, is the model for a transformer. That is the transformer. We hear about transformers. Transformers used to be very different earlier. What were they? Bumblebee and others. What were the other transformers? No one's getting the joke, I guess. You can probably explain it to them. Transformers is a movie for kids where vehicles become robots and all of that. But these transformers are different. These are a type of neural network which allow more lifelike production or output. In a very layman's term, that's how I would say that. What is the design of this? Essentially, the 101 of neural networks, which I probably should have copied over a few slides from my AI in a day. The idea of neural networks begins with the perceptron. Way back, 1965 or something like that. We were not even into the era of silicon computers. And the perceptron was an effort at mimicking the neuron. And all of these drastically failed. Till the 1980s, 1990s, these were failing. I started my work on that late 90s, early 2000, and these were failing. If we spoke about that, people would say, come on, you're talking about strong AI versus weak AI, the old terminology, sir. Whereas today we've got terms like AGI and God knows what all put in with AI. So McLaughlin, when he came up with his neural network, he said, okay, what happens in a neuron, a biological neuron, when the input potential goes to a certain voltage level, it gives you an output. There's a spike. So that's why it's called a threshold logic unit. I'll not bore you with that, but if we keep that in mind, these are called connectionist models versus symbolic learning versus connectionist learning. Now, we are trying to bring in multiple topics here, multiple threads. It will be a little challenging. We will tie them all together at the end. We've spoken about supercomputing. We are talking about models here, neural network models, and then we are going to go in and tie them together. I will also leave you with, I'm setting the expectation so that you don't sleep off. I will also leave you with the roads ahead in case you're into research and all. Possibly if someone wants to collaborate, I'm very happy. Now, these are not neurons as yet. These are way beyond neurons. We call them connectionists because you put neurons together. There is an input layer, there is an output layer. They are hidden layers, hidden units. And magic happens. What is the magic? Boltzmann did a lot of work on that, Boltzmann machine. There is the Markov model, statistical simulation. It's actually called stochastic gradient descent. Essentially, it's a convergence that is driven, a mathematical convergence if you think of it. Given any function, and they used to be optimization functions, and because these were in the domain of optimization, linear programming and all, there was a time frame. I remember when I first presented my paper, it was about adaptive topology neural networks, and the audience's first question was, when you say AI, you are talking about optimization. And it felt like I was on Venus, he was on Mars, Earth was somewhere in between, and we were not connecting. Luckily, there was a very senior gentleman, I'm forgetting his name, Professor Singh, first name I don't remember, from IIT Delhi, and he took charge. He understood I was completely off my turf. So he explained what was happening, what was going on, that he was looking at the more optimization side of things, and I was looking at the connectionist part of it. So they make layers, input layer, hidden layers, output layer, very simply put. This is like talking about these things in today's world is like talking about assembly language when you're teaching a programming class. No one does assembly, we do. Most of our coding is in assembly when we are doing at the lower level, it's actually below that, but still, it's not done in the market. Similarly, when you're dealing with these systems, you will not be dealing at these levels. You will be dealing with models directly, at the most with activation functions and layers. Still, it's good to know. All right, we take them together, then we get various layers. This one is a linear, the first input is a normalization layer, a linear layer, and then you have a matmul, masks, or softmax, you have dropouts. How did people figure these out? In my presentation, I've got another QR code which points us to a GitHub repository. I've put in my entire discussion with ChatGPT over there. You'll find lots of nice links over there. How do we work out a model? How do we make a model? Is it a shot in the dark? You take a few pebbles with lots of layers and activation function, move it around, shake it around, and pick out one. Okay, this is my next layer. No, it's not that. We know what we're doing. We know what we're targeting. Where does this come from? Essentially, you will have to go back to basics if you want to work at this level. Not necessary. You don't always have to grease the vehicle. You can drive it. Do you ever think of the person who tuned your car? Most of you would be old enough for driving, or at least bikes. Do you think of the person who tuned your bike or your car when you're driving it, when you're applying the accelerator? Next time, think of him or her, please. So then you would know what we do here. All right, so this is a transformer. Details can happen later. We can talk about that. You'll find lots of better information, people who go into the maths of it. I want to touch upon the engineering aspect, so I'm rushing a bit. What did they do? They take this transformer, 1, 2, 3. It's always good, right? You add in multiple things. Okay, it doesn't work, you put in one more. Just as an aside to keep you guys interested, I was experimenting. One of my favorite research domains is human-computer interface. So I was experimenting with smart glasses. And whatever it was, I wanted to bring the LCD closer to the eye, and remembered my class 12 optics. So I was putting some lenses together. And I said, okay, I've got 2 lenses and I'm getting this focal distance. What if I put a third one there? No maths done, no calculations done. Simply, I was trying things out. Didn't work. I'll have to go back and see what's happening. So anyway, back to the thing. It's not just put in there. It's figured out, okay, how are we planning to do this? What is the... See, the theory over there is essentially, there's a lot of theory that people are trying to fit in. Till 2 years back, people were saying, oh my God. I mean, I hate using this on the stage, these 3 words, OMG, but we cannot explain neural networks. And a good number of us from the old school, we came out and said, really? Did you build that? Oh no, I just used it. Then of course you cannot explain it. Sorry about being a little hard-headed on that. So no, this is well designed. That's why you have 3 transform blocks here. You have input, you have softmax, and you're getting an output. What is happening is, essentially the idea is to increase the entropy as we enter the model. And while we are coming out of it, ensure that we reach a certain level of predictive descent. Derives more from what is called the used to be called the A-star algorithm, finding optimal hill climbing, and now people are coming up with a perpetrated Q-star algorithm. All right, again, we are not talking about these. There are other people who can explain these better to you. Given this, a little bit on the sequence, maybe I'll go to the next and next. Given this infrastructure requirement, all right, this is a model which this can be fitted onto our regular computer with a small GPU. It can work if I just have that, what I was showing on the screen. If I just have this, it can fit onto a regular mobile phone with its Mali GPU or the other GPUs that are there. It can fit onto our desktops. Why was I actually setting the ground for HPC at the beginning then? See, we need to look at the fundamentals of AI, the way it is implemented, connectionist AI. And I hate saying this, I'm not a data science person per se, but the core, the magic lies in the data that goes into training. The kind of data that goes into training this kind of model is huge. It's like huge, humongous. It's arguably the GPT-3, GPT-4 models have a few trillion parameters. You can apply a rule of thumb like linear equations. If you have n number of variables, you need n number of equations, right? Did I get my maths wrong? No. I keep going back on that, I'm sorry. Similarly, if you have n parameters, you should at least have n, some say n times n amount of training set data entry. Now there are of course people working towards training models with lesser data, and a lot of research is happening around that, but that's the brute force method, and the brute force method works as demonstrated by OpenAI, I'm sorry, not us, OpenAI there. Now if you take a system where you have trillions of data, 3 terabytes, 6 terabytes of data, one of the corporates came out recently, I think that was IBM itself, which came out recently 2 weeks back, and they have shared the data that they have used to train their LLM. Every company has an LLM out in the market. I was trying one for ours and we don't have a supercomputer, sorry. So we use others. And the director, I believe, of their AI strategy has given the strategy they've used for reducing the data set. Now when you have a few terabytes of data, where are you going to hold it? How are you going to load it? Just to ensure that we are all on the same page here, because I went a little deep into this and the flow might have lost some of you. We have the neural networks. I'm putting the entire supercomputing discussion on hold. We have the single neuron model. We have the layers that we make out of them. We put the layers together. We get a model that can mimic a behavior. How it happens is you give it an input, you give it an output, just to ensure I've not left any gaps in between. You give it an input, you give it an output, it simply calculates what is the gradient. Y is equal to mx, the gradient for a linear model. What is the gradient that will connect the input to the output? Stochastically, like our Newton's methods and Rangakutta method and all of gradient descent, if you remember from your numerical analysis classes, that's what is happening. If you do that stochastically across millions and trillions of data points, the guess is you will find something, and they have found a lot of things. We are trying to train that, and what happens, the more number of times you repeat it, it's called an epoch in a training session. Entire data set passes through the model, forward propagation, of course, back propagation, which means adjusting the data weights. I'll not go into deeper into that, it's all common, available on the YouTube. It's probably part of your syllabus also now, I believe. It's part of the academics as well. We have to train them for multiple epochs to do what? To get convergence, reduce the error. Then there are lots of fancy things about hyperparameter training, etc. How do you run such a huge model for hundreds of runs and still be able to produce results in time? Everyone has a release cycle. We don't have ages. All right, I'm starting the training and my great grandson is going to probably find the model trained. If we do that, we can use our small mobile phones. I don't know, I don't think so, but probably it will be 10, 20 generations later if we use this. But of course, we have a time limit, we have specific deadlines in which we have to meet, And we are trying to do this with trillions of components. Moving ahead a little quick because it's becoming more of LLM discussion than the HPC for LLM. I have convinced you there is something called a supercomputer, HPC, which was the mumbo jumbo part at the beginning. I've tried to convince you that we need very big computers to train something like a ChatGPT with the trillions of parameters and trillions of these. How do we go about doing that? So this is the infrastructure requirement for LLMs on HPC. What do you need? Let's say we were to go down to our local computer bazaar, computer market here, and try and buy a system for LLMs. What would you buy? Assuming they have all the components. We can go online, right? Maybe the local shops don't have that. Should I read it verbatim? No, I don't know. Whatever is there. I was actually running a little late, so I'll be honest here. I asked ChatGPT to look at the points and put something over there. Let's just match it what it said. See, what I would first be needing is we would need GPUs because we need to accelerate it. Millions and trillions of neurons, they have to be calculated. Why were GPUs used? Because GPUs were doing just that. What were they doing? To get a frame rate. GPUs are for graphics. Graphics are used for video games. To get the frame rate at that speed, 30 FPS, 60 FPS, think of full HD, whatever number of pixels are there, 4K, 4000 pixels, they are doing that calculation, very simple calculation for the pixel. Increasing, adding a number to the RGB value, adding something to the alpha value. These are simple numbers, simple operations. At the same time, what are we doing for the neural network? Y is equal to mx. Most simple activation function. Activation function is what triggers the neuron. Go to higher order activation functions. What are we using? Let's say you're using a ReLU, GeLU, whatever. Ultimately, it's composed of very simple elements. And even if it is a complex activation function, I'll tell you in the next slide or so, and that is going to be interesting from the engineering side of things. Sorry if I'm losing you on that. These are very simple calculations. At the end of the day, computers know very simple operations. Load, store, add. That's it. Load, store, add. Is that sufficient to do any computation? I'm sorry, I'm looking at you because you're the nearest, any of the students. Load, store, add. Is that sufficient? Is that Turing complete? Turing complete is a system that can mimic any other Turing machine. I'll leave that as an open question. Go and figure that out. Okay, so what you're ultimately doing are very simple arithmetic operations. I'm sorry for the cameraman person because if I'm moving around too fast, I did not realize that. Okay. So they do very simple operations, and they have, like they were doing for graphics, they have very simple cores, what you call the CUDA cores. Each of them works on the array, and typically if you remember from computer graphics, I don't know if it is part of the syllabus these days, there are various arrays for rotation and luminescence and colors and all of that. So already they were optimized for matrix methods. Some intelligent person at NVIDIA around that time said, hey, why don't we use this for accelerating other places where matrices are used? And 1D, 2D array, higher dimensions also when we go to tensors. Google would say that, hey, for that you use a TPU, not a GPU, but still, yeah, 1 to 2D array processing essentially. So what they did was they had this multiplication and matrix methods available, not just multiplication, I'm sorry, matrix methods available, they put them together as something called CUDA. And that sort of, not that that was the beginning of it, that sort of brought in the big data revolution. Big data was about lots of data. See, I'm trying to time the threads here. We are talking about big data. All the things I spoke about was big data. Where do you run big data? On HPC clusters. How do you accelerate big data? Someone does something fancy with a GPU and says, all right, this is how we can do millions of calculations together. Now, this is not the domain we really go deeper into. GPUs are a transient phenomena. Why? I will tell you. I'm making this statement more formally because I take that school of thought. Right now, they are the winners. Now, CUDA came out somewhere around the middle of last decade, mid 2000s, around 20 years back, 15, 16 years back. And then there were other versions, and on top of CUDA, they did a fancy thing. What did they do? And this is where we get into engineering. Okay, when we're talking of a computer, we are talking about not just compute, but storage and I/O also, which includes networking. So I will not go into those right now. We're looking at compute. And a quick time check. I'll try and wrap this up in 5 to 10 minutes. So just be with me. Okay, that's a GPU, just in case you've not opened up your computer. If you've not, go and open it up. Don't tell anyone Abhishek said that. I don't want the brickbats and all coming in. So just to wake you guys up, I was in the 5th or 6th grade. Mummy was not at home. Father was there. He was at office. I had the Ambassador to myself, and that was the first system I opened up. So feel good about opening things up. Put it back together. Put it back together. He came home for lunch, had a look at it. Okay, when I come back, it should be fixed. It was. So open it up. Don't break anything. That's what you will find. That's the GPU, but it's a very simple GPU. And we left off on the question whether, sorry, if I lose out on a thread, do remind me, because this was sort of a last minute preparation, whether we can buy the components for making a supercomputer. I'll come to that after we cover BLAS. So what are the challenges? This sort of will allow me to say why the local shop or others may not have the components that you need to put that supercomputer together. What are the challenges? The first challenge is scaling the LLM. I'll leave you with a little bit of homework for the want of time. GPT 1, 2, 3, 3.5, 4. What is the size scaling? Look at that. It's a exponential. It's not a linear graph. Keep adding, you keep adding, you keep adding, and now we are actually going against that philosophy now because it's not very practicable. There are other sustainability issues to that. So challenges in scaling, you understand scaling. Solutions such as optimized algorithms, parallelization, hardware advancements. Parallelization is divide and conquer. What is divide and conquer? 10 things to solve, 100 things to solve, 10 people to solve it. Give each 10 and you'll get it done in 1/10 of the time. I was expecting objections from the students here. 100 items to solve, you with me? 10 people to solve them. We divide them, 10, 10, 10. So the time taken should be 1/10. Okay, do that as a homework, but no, it will not, because you'll have to go and hand out the question paper and collect it. Essentially what we call the distribute, scatter, gather, and all of those terms that come in there. So parallelization, and everything cannot be parallelized. You still have scope in algorithms, data structures. I hear fancy things saying, oh, algorithms are all done and dusted, data structures are all done and dusted. Really? Explore that domain. And of course, I will be touching on that. We have the new entity, new elephant in the room called quantum computing. A new plethora of algorithms coming up for that. Alright, so optimized algorithms. What are you optimizing? And typically, remember, I'm the person who greases the vehicle. Anyone with me? Right? So, I mean, okay, not in this. We probably wear a dungaree and go in and grease the computers. Don't try that on a real computer. It will go up in fire. So this is the creature, BLAS, which actually enables the acceleration. This will be the last technical deep dive that I do here. I want to talk about a few future directions, and I mentioned that. What is BLAS and what does it do? See, BLAS goes way back to the 1970s, I believe, and we are really talking about history here. Things from even before we went to school, things from before we were born, many of us. So, if a digital computer is solving anything, what is it doing? Old question. Add, load, store, add. Is that Turing complete? No, I'm not answering that. Hold on, you go and do the homework on that. Load, store, add. Is that Turing complete? How would you do a subtract? How would you do a subtract? I'm adding to that question, okay? I must mention there was one gentleman, he's no more, Professor Chaudhary. And I was a 8th grader, very interested in programming. He sees me sitting in with the chipping in book by brother Eric D'Souza and says, okay, do you know what are variables? I used to call him uncle. I said, yes. Good. Can you put value into 2 variables? I was like, what does he think? I'm a kid? I was a kid. I said, yes, show it to me. And then like basic used to be let A is equal to 1, B is equal to 2. Okay, good. Swap their values. I said, yes, C is equal to A, B is equal to whatever comes after that. He said, okay, do this without using C, without using a third variable. Tried that? That's where your algorithm should start from. Swap two values without using a third variable. Back on the topic, what is BLAS? Essentially, they are doing very simple arithmetic. Why? Matrices. Matrices and discrete methods are the fundamentals of any numerical problem that is solved on a computer. Everything is brought down to matrices. Don't quiz me on it. It's difficult talking in front of professors because I might get quizzed on my matrix mathematics, what I remember of that. But if you look at it, what happened in the 1970s was because there were so many implementations, and those were the era of Fortran. Any of the students here, have you heard of Fortran? I must be getting old. Students these days don't even hear about Fortran. Fortran stood for formula translation. It was the initial programming language that was used for numerical methods. COBOL was more of a business application and Fortran was more like scientific. And NIST, whatever that organization is, came out with a set of standard matrix interfaces, matrix methods, matrix mathematics, whatever you call that, interfaces for doing things like matrix addition, subtraction, multiplication, whatever other matrix operations. I'm sorry, I was looking for that word. And that became BLAS. That was the first layer. And BLAS has levels where you do the operations on vectors, matrix to matrix, vector to vector, vector to matrix, matrix to matrix. These are very standard definitions, and because the standard definition existed from NIST, it took on, and most of the scientific software was written using the BLAS interface. Now, 101 of programming, I'm so sorry, but you'll have to bear with these 101s here. What do we call it when in programming we create a layer of interface behind which we can change the libraries? It's called an abstraction layer for the want of time. This is not a lecture session here, I'm so sorry. Feels so good, right, coming on here and then people are listening to you. So, BLAS is like an abstraction layer. It is an abstraction layer, not like. And what we do is, BLAS remains common. Because the interfaces have been defined, it's called ABI. Like you've got the API. If you're not familiar with ABI, go look that up. You can really impress someone if you can go and talk about ABI really nicely, if you're going into the industry. ABI is Application Binary Interface. How do you place your program in memory? How are the function calls made? I would want to take questions with students around, but then you put things on the stack, and when the program jumps back, you have things coming on the stack and all of that stuff. So, BLAS is an abstraction layer on which, behind it, we fill in the libraries with which BLAS is implemented. A very common implementation of BLAS is called Open BLAS. When you get a new computer, not as in buy, when you design a new computer, it's called bring up, a new system bring up. When you design a new computer, okay, up for time. When you design a new computer, you optimize BLAS for that. How do we ensure portability? Good old C. Good old assembly language? No. Assembly is very system specific. Good old C interfaces, these days probably Python interfaces, other languages, but Python does not work at the systems level. I'm sorry, as a systems programmer, we have to talk about things that it does not satisfy. It's a good language, good platform for prototyping, etc. So go and implement and optimize BLAS. Are you with me on this? Because this is probably what I could have just spoken about 5 minutes and done. All right. HPC for LLM, this is what my presentation would have sounded like. From here, start. All you do is you go to a system, sorry. You go to a system, you take the BLAS, you optimize it, and you optimize it by ensuring, mark my words here, sorry. You optimize it by ensuring the cache lines, the CPU architecture, the cache lines are properly populated, period. That's it. Why? L1 to L2 cache, there is a 1000x access time delta difference. L3 don't even talk about it, systems don't even implement it. Then they come in factors like NUMA, non-uniform memory architecture and all. This is one area you should really explore. How do we get BLAS to be optimized on any system? So what did we talk about? We spoke about ABIs and we spoke about BLAS. I did speak a lot of mumbo jumbo about HPC and all. That's available in the market. You can find those small books which tell you about it. These things, I don't think people talk about it as much in the industry and should be part of it. In the other outside the industry. I will not go into these, measure the performance and all. Typically how we measure it is not very different in terms of, there is of course when you're talking about LLMs, there is the performance of the prompt engineering. I'm not going into that. Prompt engineering is, I gave it a prompt in natural language, it understood it and gave me a response. How does it converge? There are parameters, standard tests are there. Those can be found, and this is a living document. It's on Google Docs. Okay, that's another corporate I'm mentioning. I'm sorry, I hate mentioning corporates. So this is on Google Docs. I'll keep adding to this. Ultimately, if you can ensure your BLAS is optimized, and how do we measure BLAS optimization? We measure it by running packages like LPAC and LINPAC. When you hear about the top 100, 200 supercomputers, when you hear about the number one supercomputer, what they have done is they have optimized BLAS and greased it to the maximum extent possible. So that's the kind of grease we apply. All right, so future trends and what comes in there. How does BLAS work faster? I'll quickly touch upon that. This is the end part of it. Quickly, maybe if we have time for questions, I'll take those. See, even with GPUs, what is happening is more and more parallel processors are added. Bigger matrices, split them up. Great. Google comes up with TPUs. A tensor, I was refreshing my maths with ChatGPT, is a higher dimensional matrix. A matrix, two-dimensional matrix is a convergence on the tensor. Thank you for, did I get my maths right there, sir? So Google comes up with a TPU and you can actually deal with higher dimensional tensors. Still parallel processing. Okay. How do we parallel process even better? Good. We'll jump onto the domain of quantum parallelism. What happens in quantum computing? Entanglement. What is that? What did Einstein call it? Spooky work at a distance. Entangled photons, they work at a distance. But no, as I understand from quantum informatics, you cannot use that for conveying information. Quote unquote, it's doubtful. People into quantum physics or advanced physics would know that better. But still, quantum algorithms give us the benefit that the non-determinism in that algorithm. When we don't call it algorithm, we call it a circuit, depending on the school of thought that you're looking at it, algorithm or circuit. I believe in the quantum circuit school of thought. They give us a non-determinism. The benefit of non-determinism is already seen in our computer architecture as it exists today, in the terms of out-of-order execution, etc. Quantum processors, when implemented, take that to the next level. Quickly to touch upon that, you have a if-else statement. How many paths can be taken? 2. What if you pre-calculate both of the paths? If A is equal to 1, B is equal to A plus 2. If A is equal to 2, B is equal to A plus 3. If you can pre-calculate, calculate beforehand, you are guaranteed it becomes a O of 1 algorithm, not even an O of n. It's an O of 1 algorithm. The entire path through the program is predictable. So go into quantum computing, that's another option. The other aspect of that is neuromorphics. Very different, where we try and go beyond the McLaughlin's model of the perceptron and we say, okay, how are neurons working in the human brain? And we try and implement that in silicon. So that's called neuromorphics. My specific research domain is something called quantum neuromorphics, where I'm trying to implement quantum circuits for neuromorphics. Both are there. Lots of people are getting into the field now. The other interesting part, which I believe Microsoft Research here or in Bangalore has done very nice work on, that is DNA computing. Because of the information density that DNA has. DNA is the building block of life. I don't know, some of you may not be biology students, so you might say, what are you talking about? So these are some areas, domains that you can look at, but the holy grail, I'm sorry, it's not in a religious context, I don't know, for a better term, the real magic behind creating HPC is BLAS optimization. You optimize BLAS and everything works fine. That's an over generalization, because you do have other elements, and why I leave you here. The other elements are network speed, network latency, network bandwidth, storage, etc. All of them matter. And why I leave you here is, we are today in the world of 5G. I don't have, but if I just change my mobile, I'll get 5G. Our government is talking about 6G, whenever the definition happens. And any of you familiar with networking here? I'll give you quickly. We talk about the bandwidth, the Gbps that you're getting. Latency is also important, because when you're dealing with computer architecture, you're moving data around within the system. Now we're talking about moving data from one node, one computer to another. We're talking about parallel organization. I did not tie in a few things, I'll try and tie those in quickly, 1 or 2 sentences. With something like 6G, we can put mobile phones together, combine them into parallel architecture, and implement public infrastructure supercomputers. The reason I put this site on here, this slide on here, is since I had done the discussion with ChatGPT, the data was ready. I put that onto GitHub. It's a project that we are trying to seed now, where we will try and utilize 5G and 6G to put together a public infrastructure supercomputer for running these workloads. How it will pan out, I don't know. Contribute, come and join in. Final statement. How would you go and purchase the infrastructure? See, what you need is the best GPU you will get, or the best accelerator you will get. Do a search for that online if you're putting together a supercomputer. How to do the models and all will get very complex. We have to end it here now. Look for the fastest GPU that is available. A good number of them are available on free platforms like Google Colab. Get the model that you need from places like Hugging Face. They have a lot of nicely trained models. Download them. You'll also probably find some example notebooks. In case you're familiar with notebooks, you should familiarize yourself. Execute it. Then look at the entire infrastructure I spoke about. There'll be lots of questions. If now or later, feel free to reach out to me. Thank you. Sorry if I took extra time. If there are 1 or 2 questions I can take, or I don't know, how's the time doing? Yes, anything I missed out specifically?
You said to remind us about supercomputer and GPU.
Okay, supercomputers and GPU, see, typically it's a challenge in the market. You'll have to look at the market dynamics. Now, I really encourage, especially the students here, to really look at what's happening in the industry. And it's public knowledge, so I don't mind saying, look at who is acquiring who. Which company is acquiring which company. So which makes the best GPUs today? No doubt it's NVIDIA. What did NVIDIA buy? NVIDIA bought Mellanox. Mellanox is a networking company. Why are they buying it? You see the reason here on board, what I told you. They are looking at infrastructure to do better I/O. So you will have to follow these companies, typically follow NVIDIA. They have a lot of nice written material. I think they have something called a CUDA school or something. They have a lot of nice material. Pick up the basics on that. The typical GPU that is used today is called the A100. That is from NVIDIA. But there are lots of there are a lot of other accelerators that are available. You should be familiar with those, like the True North accelerator. It's called ASIC. Again, I'm going back to my old company's reference, but that's from IBM. There are lots of similar accelerators that are available. So if you look at them, you will find lots of resources online. For the want of time, I'll just cut it here. And you can put your, I wanted to do this, but maybe let's see on this slide deck I'll put it. You can put together your supercomputer today in a matter of few hours. Online, not in terms of performance, in terms of functionality. In terms of functionality, I clarify myself. It's okay, you said few hours, where's the money, where's the infrastructure? No. You want to figure out how the OpenMP works. OpenMP is MPI, message passing interface. Okay, good. It's part of your syllabus?
Yes.
Wonderful. I bow to your syllabus design, sir. Thank you. Because earlier, is it a part of standard syllabus these days?
Yes, sir. Parallel program.
Must be a fourth year elective.
No, sir. Third year. First year.
Wow, I would be concerned sitting in the classroom here. I would have to go and revise. So yes, OpenMP, you can look that up. You can put together your Docker containers, your virtual machines, figure out how the message passing works, and then go into the nitty-gritties of the system, and it can be delved deeper into. I tried to answer that the best I could. Any other questions?
Sir, it was very amazing speech, sir.
Thank you.
Thank you.